California has earned a reputation as earthquake country. Mention the San Andreas Fault almost anywhere in the world, and people immediately recognize the name. Some have also heard of the Hayward Fault, the San Jacinto Fault, or the Cascadia Subduction Zone farther north. Yet hidden among these famous geological features lies another fault that receives remarkably little public attention, despite stretching across much of Northern California and possessing the potential to generate an earthquake powerful enough to reshape the landscape. It is known as the Bartlett Springs Fault Zone, and despite its relatively quiet behavior during recorded history, many geologists consider it one of the state's most intriguing and least understood active faults. Fresh attention has now turned toward this overlooked fracture after a series of earthquakes struck the rugged mountains northwest of Covelo, California. Within less than a day, the area experienced a magnitude 4.0 earthquake, followed by a magnitude 3.9 event, and then a magnitude 4.4 earthquake at shallow depths of only a few miles beneath the surface. According to the earthquake locations released by the United States Geological Survey, all three events occurred approximately 31 kilometers, or about 19 miles, northwest of Covelo, raising immediate interest because the sequence lies close to the mapped trace of the Bartlett Springs Fault Zone. Officials reported no significant damage, but the earthquake sequence quickly reminded scientists that this little-known fault remains very much alive. At first glance, earthquakes in the magnitude 4 range may not seem especially remarkable. California experiences hundreds of earthquakes every year, most too small to attract widespread attention. Yet the location of these recent events matters far more than their size. They occurred along a fault system that has puzzled geologists for decades. Unlike many of California's better-known faults, the Bartlett Springs Fault has remained unusually quiet during the historical era. That silence, however, should never be mistaken for inactivity. The fault zone extends for more than 170 kilometers, or approximately 108 miles, through the northern coast ranges of California. It forms an important member of the greater San Andreas Transform Fault System, although it occupies the eastern side of that complex network, rather than the famous main trace that slices through central California. Geological mapping has shown that the Bartlett Springs Fault connects with several other active faults, creating an intricate web of fractures that collectively accommodate the slow but relentless movement between the Pacific Plate and the North American Plate. Understanding why this fault exists requires stepping back millions of years into California's remarkable geological history. The landscape visible today did not simply appear in its present form. It emerged through an extraordinary sequence of tectonic events involving subduction, volcanic activity, mountain building, and eventually the sideways motion that defines much of modern California. Long before the San Andreas Fault became the dominant feature along the western edge of North America, oceanic plates plunged beneath the continent. That ancient subduction system produced immense pressures that folded rocks, uplifted mountain ranges, and left behind countless fractures deep within the crust. Many of those ancient weaknesses never completely disappeared. Instead, they became natural pathways along which newer tectonic forces could later concentrate. The Bartlett Springs Fault appears to be one of those inherited structures. Modern geological studies suggest that an older fault created during ancient subduction was eventually reactivated as the Pacific Plate began sliding northwest relative to North America. Rather than creating an entirely new fracture, Earth's crust reused an existing weakness. That long geological history makes the fault especially fascinating because it preserves evidence of multiple chapters in California's tectonic evolution. Its position also makes it unusually important. The Bartlett Springs Fault occupies a transition zone where different tectonic processes overlap. To the north, deformation remains influenced by the subduction of the Gorda Plate beneath North America, part of the broader Cascadia Subduction Zone. Farther south, the region becomes increasingly dominated by strike-slip motion associated with the Pacific Plate sliding past the continent. The Bartlett Springs Fault effectively serves as part of the bridge between these different styles of tectonic movement, helping distribute enormous stresses through Northern California's crust. That role becomes clearer when viewed alongside neighboring faults. West of Bartlett Springs lies the Mahakama Fault, another active right lateral strike slip fault. Farther west still stands the legendary San Andreas Fault itself. Southward, the Rogers Creek Fault continues toward the densely populated San Francisco Bay region. Together, these faults share the burden of accommodating plate motion measured not in yards each year, but in mere inches or several centimeters annually. Although the movement is slow enough to escape direct human observation, it never stops. Every passing year adds another tiny amount of displacement. Every century adds several feet or more than 1 meter. Every millennium transforms entire landscapes. That gradual movement explains why earthquakes occur at all. The rocks forming Earth's crust are remarkably strong, but they are not infinitely flexible. As tectonic plates continue moving, enormous stresses accumulate inside the crust. For years, decades, or even centuries, rocks bend almost imperceptibly while storing vast amounts of elastic energy. Eventually, the strength of the rocks is exceeded. A sudden rupture releases the stored energy within seconds, producing seismic waves that radiate outward through the Earth. Most Californians associate that process almost exclusively with the San Andreas Fault. Yet exactly the same physical principles apply to the Bartlett Springs Fault Zone. The difference is that Bartlett Springs behaves in a way that is far less straightforward. One reason scientists remain fascinated by this fault is because parts of it appear to creep. Fault creep sounds almost harmless, but it represents one of the most intriguing behaviors observed in earthquake science. Instead of remaining completely locked while stress builds for centuries, certain portions of a creeping fault slowly slide without producing major earthquakes. Imagine placing two rough wooden boards against each other. One board moves only after tremendous force suddenly breaks the friction, while another begins sliding gradually under steady pressure. Faults can behave in surprisingly similar ways. Measurements collected from geological studies have identified evidence that sections of the Bartlett Springs Fault experience this slow, continuous movement. Rather than storing every bit of tectonic stress for a future earthquake, those creeping portions release part of the energy little by little. The movement is measured in fractions of an inch or millimeters each year, far too slow for people to notice directly, yet significant enough for scientists using highly sensitive instruments. At first glance, that may sound reassuring. If the fault releases stress continuously, perhaps it cannot produce a devastating earthquake. Unfortunately, nature is rarely that simple. Modern satellite measurements and high-precision global positioning system observations indicate that the entire Bartlett Springs Fault is not creeping uniformly. Some segments appear to move gradually, while others remain stubbornly locked. Those locked sections continue accumulating tectonic strain year after year. They function like tightly compressed springs hidden within the crust, storing energy that cannot escape through slow motion alone. That discovery transformed scientific understanding of the fault. Rather than viewing Bartlett Springs as a harmless creeping fracture, researchers now recognize it as a complex system containing both slowly moving sections and dangerous locked patches. Computer simulations of earthquake ruptures suggest that these locked areas retain the potential to generate major earthquakes, although the creeping portions may influence exactly how future ruptures begin, propagate, or eventually stop. The result is a fault that refuses to fit neatly into traditional categories. Its historical earthquake record only deepens the mystery. During approximately the last 150 to 200 years of instrumental observations and written history, no truly large earthquake has been confidently attributed to the Bartlett Springs Fault itself. The strongest directly associated earthquake occurred near Lake Pillsbury during August of 2016, reaching approximately magnitude 5.1 and producing an energetic aftershock sequence. Even that event represented only a modest release of energy for a fault stretching more than 108 miles or 170 kilometers across Northern California. For many people, such a quiet record naturally leads to an important question. If this fault is truly capable of producing powerful earthquakes, where are they? That question has no simple answer. Instead, it opens one of the most compelling scientific mysteries hidden within California's mountains. The search for that answer has taken scientists far beyond modern earthquake catalogs and deep into the prehistoric landscape of Northern California, where the rocks themselves preserve evidence of earthquakes that occurred centuries before anyone kept written records. Every cliff face, offset stream, fractured ridge, and buried layer of sediment has become part of a geological archive, quietly recording violent moments that unfolded long before the first settlements appeared in the region. Unlike hurricanes or floods, earthquakes leave behind very few eyewitness accounts that survive for hundreds or thousands of years. Instead, researchers rely on paleoseismology, the science of reconstructing ancient earthquakes by examining the physical changes they left in the ground. Across California, this work often begins with trenches carefully excavated across active faults. Each trench exposes layers of soil and sediment that accumulated over hundreds or even thousands of years. When an earthquake ruptures the surface, those layers become broken, shifted, tilted, or buried by younger deposits. By studying these disturbed layers and determining their ages through radiocarbon dating and other geological techniques, scientists can estimate when ancient earthquakes occurred, even if no written record exists. It is painstaking work that sometimes requires months of analysis before a single event can be identified with confidence. Yet these investigations have completely transformed the understanding of faults that once appeared deceptively quiet. The Bartlett Springs Fault Zone is one of the clearest examples. Although modern earthquake records suggest only moderate activity, geological evidence points toward a much more dramatic past. Studies indicate that this fault has generated earthquakes far larger than anything documented during California's historical era. Some seismic hazard assessments estimate that the fault is capable of producing a characteristic earthquake approaching moment magnitude 7.6, while more recent mapping by the United States Geological Survey classifies major sections of the fault as capable of generating earthquakes around moment magnitude 7.0 if extensive portions rupture together. Those estimates place the Bartlett Springs Fault among the significant earth courses in Northern California, despite its surprisingly modest historical record. Perhaps the most remarkable discovery involves evidence for a powerful prehistoric earthquake that occurred sometime between approximately 300 and 1,000 years ago. That enormous range reflects the natural uncertainty involved in dating ancient geological deposits. Yet even with that uncertainty, one conclusion remains remarkably consistent. A very large earthquake appears to have ruptured the fault centuries before modern California existed. No newspapers reported it. No seismographs recorded it. No photographs captured its destruction. Yet the Earth preserved enough clues for scientists to recognize that it happened. The implications extend far beyond simple historical curiosity. Human memory often creates an illusion of safety. If a fault has remained relatively quiet throughout living memory, communities naturally begin assuming it is unlikely to produce a major earthquake. Geological evidence repeatedly demonstrates that this assumption can be dangerously misleading. Many active faults operate on timescales measured not in decades, but in centuries. Entire civilizations may rise and fall between successive major ruptures. That perspective changes the way earthquake hazards must be evaluated. Instead of asking whether a fault has produced a large earthquake recently, scientists ask whether it possesses the physical characteristics necessary to produce one at all. Fault length, rock properties, accumulated strain, long-term slip rates, and evidence from prehistoric ruptures often reveal far more about future potential than modern earthquake catalogs alone. The Bartlett Springs Fault scores high on nearly every one of those measures. Its length alone immediately attracts attention. Earthquake magnitude is influenced by several factors, but one of the most important is the size of the fault area that ruptures during a single event. Longer faults generally have the ability to generate larger earthquakes because a greater portion of the crust can suddenly break and release stored energy. Although not every rupture involves an entire fault, the Bartlett Springs Fault extends more than 170 kilometers, or approximately 108 miles. placing it well within the range capable of supporting powerful earthquakes under the right conditions. Length, however, tells only part of the story. Equally important is the type of movement occurring along the fault. The Bartlett Springs Fault is classified as a right lateral strike slip fault. Imagine standing on one side of the fracture while looking across it. During an earthquake, the land on the opposite side would appear to move toward the right. That style of motion is identical to the movement occurring along the San Andreas Fault and several other major faults throughout California. Although the movement sounds simple, the forces responsible are immense. The Pacific Plate continues its gradual northwestward journey relative to the North American Plate. Their average motion amounts to only a few inches or several centimeters each year, roughly comparable to the rate at which human fingernails grow. Yet these tiny annual movements accumulate relentlessly over centuries. Rocks that refuse to slide smoothly instead deform elastically, storing energy until friction can no longer hold them together. Eventually, the accumulated stress exceeds the strength of the fault. Within seconds, years or centuries of stored motion are released. Entire hillsides may shift several feet or more than 1 meter. Roads can split apart. Streams may suddenly change course. Seismic waves race through the crust at thousands of miles or several thousand kilometers per hour. The slowest geological process suddenly becomes one of nature's fastest. Yet despite those well-understood physical principles, one characteristic continues setting the Bartlett Springs Fault apart from many of its neighbors. It does not appear to behave consistently along its entire length. Researchers using satellite observations, field mapping, and global positioning system measurements have discovered that different segments of the fault appear to release tectonic stress in remarkably different ways. Some portions exhibit measurable creep, allowing gradual movement to occur without generating destructive earthquakes. Other sections remain locked, behaving much more like the San Andreas Fault, where stress continues accumulating beneath the surface. This uneven behavior creates one of the greatest challenges in earthquake science. A uniformly locked fault behaves relatively predictably from a mechanical perspective. Stress builds until friction fails. A uniformly creeping fault gradually releases much of its energy over time. The Bartlett Springs Fault appears to do both. That combination complicates efforts to estimate future earthquake behavior because creeping segments may interrupt rupture propagation while locked patches continue storing dangerous levels of strain. Scientists refer to these highly stressed regions as asperities, areas where friction remains especially strong despite ongoing plate motion around them. Computer models suggest that earthquakes beginning within one locked section might stop after encountering creeping portions, limiting the overall magnitude. Other simulations indicate that sufficiently energetic ruptures may jump across creeping intervals and continue propagating into neighboring locked segments. Both outcomes remain physically possible. Nature alone decides which path an individual earthquake ultimately follows. This uncertainty explains why earthquake forecasting remains one of the greatest unsolved challenges in earth science. People often imagine that scientists simply need more instruments or better computers to predict earthquakes accurately. The reality is far more complicated. Every fault consists of rocks with slightly different compositions, strengths, temperatures, fluid pressures, and microscopic fracture patterns. Conditions can change dramatically over surprisingly short distances beneath the surface. Even faults sharing similar lengths and slip rates may produce completely different earthquake histories. Some generate frequent moderate earthquakes. Others remain silent for centuries before unleashing catastrophic ruptures. Still others release much of their motion through creep, while occasionally producing damaging earthquakes from isolated locked sections. The Bartlett Springs Fault seems to incorporate elements of all three behaviors. That complexity makes every new earthquake sequence scientifically valuable. When the recent earthquake struck near Covelo, researchers immediately began examining whether the events represented ordinary background seismicity, a localized swarm, or a classic main shock aftershock sequence. Such analyses involve comparing earthquake locations, depths, focal mechanisms, timing, and statistical behavior with previous activity observed along the fault. At present, there is no scientific evidence indicating that the recent magnitude 4.4 earthquake serves as a foreshock to a much larger event. That conclusion is important because the word foreshock carries a meaning that differs from how it is commonly used. An earthquake is classified as a foreshock only after a larger earthquake occurs nearby. Until then, every earthquake initially stands as an independent event or the largest earthquake within its own sequence. Only with hindsight can scientists determine whether an earlier event actually preceded something larger. Statistically, the overwhelming majority of earthquakes around magnitude 4 remain exactly what they appear to be: moderate earthquakes followed by smaller aftershocks or isolated seismic activity. Only a relatively small percentage later become recognized as foreshocks. Unfortunately, there is currently no reliable scientific method capable of identifying which earthquakes belong to that minority while the sequence is still unfolding. That limitation often frustrates the public, yet it reflects the extraordinary complexity of Earth's crust rather than any lack of scientific effort. Every earthquake teaches researchers something new. Every sequence adds another piece to the puzzle, and every quiet fault has the potential to reveal surprises hidden beneath centuries of apparent silence.